Okay, we are starting in less than a minute. In 5 seconds per se. Okay. So while everybody is back, our next presentation will be about extreme scale earthquake simulation with MVAPICH, and it will be presented by Dr. Yifeng Cui, who heads the high performance geocomputing lab at SDSC, and helped to establish the Southern California Earthquake Center as a world leader in advancing high performance computing and earthquake system science. Cui's groundbreaking work includes enabling TerraShake, Shakeout, and M8, some of the worst case scenarios on San Andreas fault, revealing order of magnitude LA waveguide amplification. He is a recipient of several HPC awards, including in 2015 NVIDIA Global Impact Award, and 2013 IDC HPC Innovation Excellence Award, and 2009 and 2011 SciDAC OASCR Awards. He also directed an Intel Parallel Computing Center on earthquake research. Cui earned his PhD in hydrology from the University of Friedberg, Germany. So without further ado, welcome Dr. Yifeng, and please proceed.
Thank you for the introduction, and thanks for the invitation for this opportunity. Speak here. We have quite a long history working with MVAPICH team. So before I introduce our work collaborating with the MVAPICH team here to accelerate our application, I want to go through a few steps how we change the code, optimize the code over the last few years, and also some scientific background. So you see, this is quite a big collaborative effort, involve the HPC centers, involve universities, including the OSU, and also industrial vendor. So why we want to run a high resolution, high frequency simulations? If you look at the seismic band, it's from 10,000 seconds in period to a fraction of seconds in period. So, but engineer interest is typically from 0.1 hertz to 10 hertz. So that's related to the tall building, from tall building to house, and to the steel structure, which is the nuclear power plant. And currently, the regional scale, large scale simulation is still at 4 hertz. And for the seismic analysis, hazard analysis is roughly at 1 hertz. And you see there's still a long way to go to get the engineer interest at 8 hertz or 10 hertz. So from 1 hertz to 10 hertz, the computational requirement will be increased roughly by 10,000 a factor. So that's still, even the exascale machine is not big enough. So on the other side, when we move to high resolution simulations, we also needed to validate physics, and there are more physics need to be, added to the codes. So two features, for example, it's the state of art, frequency-dependent attenuation, and also the multi-surface non-linearity. So these are very important to the code for the accuracy, and I am going to introduce the code ADAPT, and that has both features, probably not the other codes available in my understanding. So ADAPT PLDC and stands anelastic wave propagation. So many people ask, what is ODC meaning? It's ocean, bay, and tree, three primary code duet, and when this was created as a CPA code. So this code is with Elastor dynamics equation to solve cobalt system of PDE, second order in time and the fourth order in space. And there's quite a few different features. And the memory variable is an important one. it's coarse-grained. It's with one single relaxation time represented at another point. So that's highly efficient and also is accurate. So the other feature is about dynamic rupture. That's only in the CPA code. We have two kind of bundling conditions. One is called a PML, perfect match layer. So this is only used in the CPA code. That's apply and damping separately for the wave field. It's some issue with the load imbalance. And the other method is called Surgeon. It's based on the sponge layer. It's unconditionally stable. So that's more load balanced, but the code is only implemented to the GPA code. So each bundling condition has kind of the upside and downside. So if you look into the code, the evolution over the years and the last 20 years, compared to the top system in the world, in the country, and including the CPA code like Frontier here, we're showing the GPU machine is now AMD Frontier. So you see the code catch up in terms of the flops and the performance. To us, it's time to solution is the most important one. And this is a code used by SCAC, Southern California Earthquake Center, for large scale simulations. Typically, this code uses 200 to 300 million core hours a year from inside allocation and also the air rack allocation, for example, from Frontier. So that's a community code. It's not a benchmark code. It's quite actively used in the real production one. So let's look at a few milestone simulation we did. And the first one is about AMD simulation. That was did from 2010. Was around wall-to-wall scenario for the southern San Andreas fault and up to 2 hertz. So we have 2 steps here. In first step is running the dynamic rupture simulation using different code called SORT. And the second step is using the PLDC code doing the wave propagation. So this was, DK's group was part of this MA simulation effort. So at the Supercomputing 13 in Denver, and when celebrated 25 years supercomputing, and this simulation, MA simulation was highlighted, as a milestone HPC analysis events. So 2016, we switched, it's still 2 steps running simulation, but the second step we now run on GPUs. And at that time was the blue water machine compared to node level. The GPU code is roughly get 5 to 6 times speed up. So that's quite efficient. So this is running a single surface nonlinear simulation. So it's a drag plague based and the simulation. And what you see, the simulation on the left side is the linear case, and the right side is the nonlinear case. So the linear case, you see the quite significantly high frequency signals. But from the right side, you see the green color is they're converted to the permanent plastic deformation. So that's how this ground motion has been reduced in the area. And this code is efficient, but the computational part is more, more workload. So this year we did run on the Frontier, and that was on 4 machine scale and running for pretty much almost 1 day. And so unlike what we did before, this is a dynamic modeling, combine the dynamic rupture simulation with wave propagation in a single step. So in terms of time solution, this is more efficient. So what you see here, it's the y direction velocity is propagate, and from the towards the northwest direction. And what we see here is chain of sedimentary basins can form effective waveguide, so that the channels love waves along the southern edge of the San Bernardino and the San Gabriel Mountains. So the soft basin can, seismic energy injected to them can rally around, causing very enormous motions, particularly in an area like Los Angeles, where building and the people are concentrated. So behind this multiple simulation is the checkout scenario. So checkout scenario started from 2008. So when we started from the 1 Hz simulation, and actually at that time, the first checkout 1 Hz simulation was done on Ranger and with the MVAPICH. If history is written about that part, because this is quite now well-known checkout scenario. It's used for largest emergency response exercise. Now it's happening every year. And last year, for example, 45 million people participating. It's also used as scientific basis for the LA Seismic Safety Task Force report. So now Los Angeles has a mandatory retrofit program. So what we designed here is the worst scenario, and for the rupture initiated from the Bombay Beach near the Southern Sea towards the northwest direction, so that you have the major impact to the Los Angeles area. So it's one of the worst scenario in the big one. So the CPA code, this is from a paper from Supercomputing 2010. This talk about the the workflow and how we do the 3D decomposition and how we do the mesh partitioning and also the source partitioning, and using some parallel I/O feature. And part of the I/O feature was converted later to a library, separate library, which is funded by NSF SI2 program. So on the GPU side, we do things now differently. Unlike the CPU side, we do now the 2D decomposition. So in this way, we have the entire column, the NZ column, available to move to the GPU side. So that increased volume communication, but reduced the communication from 6 sides to 4 sides. That's more efficient. On the GPU side, the entire column you cannot fit into the GPU memory. That's the reason we have the decomposition again, and this time it's on the N, Y, and Z direction, so that we have the better cache hit rate. So each thread, you will calculate the entire NX, the column for giving N, Y, and Z. And all threads in the same warp will have the access to the data along the fast Z. So that's what this is designed. And on the single GPU optimization, we try to improve the occupancy in the computational kernel and also the locality. For example, what we did here is defined 4 private registers, and so along the travel direction from X, like example here, 4 panels. So then utilize the pipeline copy between the register, so that 75% of the the memory access will be reduced, so causing good speed up. And that time, 2012, we were using the firming based on the firming architecture. There was 2 different configurations, and between the peripheral L1 and the shared memory or shared memory, and prefer shared memory rather than L1. We picked the peripheral L1, so because the bundling, the goal here was the bottleneck in terms of fetching the data to the memory. So we do also handle with the Gauss here. In the traditional way, the Gauss here is like 2 layers. In each iterations, you have 2 exchange, velocity exchange, and also the stress exchange. So we limited the stress exchange, so to increase the extra layers for the gross-air communication. So because we have 3 velocity variable and 6 stress variable, reduce the stress variables, basically communication, we need only 1/3, right? Improve roughly 67%. So that's one thing we did with communication. The other thing is about the communication computing overlap. What you see here on the bottom the figure, and we started calculating the bundling part from the X direction. When this is finished, using the CUDA memory copy, send it to the CPU side, and then you start transfer communicate to the other nodes. And then you, at the same time, you do the calculated now the Y direction, the bundling, and then you start to calculate the interior part. When you finished with the interior part, and the communication is already finished. So if the network is fast enough, so this will be completely overlapped. So, so that's become quite effective. I will show you the results. And that was for the linear code. And then we have the nonlinear code. And in 2016, and so this is still showing the linear code, but we, if we, because added some 3D variables, extra variables, we have to now to increase from 4 layers to 8 layers to eliminate the stress communications. And that will cause some overhead causing scaling issue. And for that, we added 2 additional CUDA thread synchronized layers so that we can eliminate 4 layers communication. So to the end, basically, we still have 4. We have kept the 4 layers communication for the gross-air. So that cost, basically at the end, we get a good performance like what we did on linear code. So, but with the nonlinear code, go ahead. Mm-hmm. Sorry. Yeah. So data are all on in the memory. Data are all in the memory. It is contiguous. Yeah. Yeah. So then with the Yifeng code actually, so it introduces lots of computation there because in each iteration, you will have basically multiple yield numbers surface. And it depends on how many yield surfaces we pick. And typically for good accuracy, we pick between 10 to 30. So basically for each iteration, you will have 10 or 30 loops again. For each loop, you will have updated the stress and at each element point, and depends on their lambda parameter and also particle velocity. So that's lots of work. So compared to linear code, you have 20 to 30 times roughly computational requirement. And also for the memory part, it's increased from roughly 5 to 13 times the memory requirement. Depends on the setting, how many yield surface you pick. So 2017, we ported the code to night landing. And we know that quite some applications have issues supporting to night landing. We were pretty lucky. We use a third-party, vector forwarding the tool called YASC, developed by Intel developer engineer. So this is quite effective, and so we can originally the code you have 9 out of cache memory access. Now using this vector forwarding approach, we reduced to 5, which is 1.6 times speed up. So with that, we were able to get like 97% of the performance we were getting from the GPUs. So keep this code is pretty running well on night landing. So now the YASC with the new Safari Rapids with the HBM, it's going to get 3 times speed up compared to the Ice Lake. And if we have the LRP now implemented with the new YASK API, we will be able to get really good performance on those kind of system. And we have not done yet, and because the YASK has changed in between, and between 2017 now, and they have now API, and we needed to port this code again. So the code has also some other changes, and for example, the discontinuous mesh. This is led by Kim Olsen at the San Diego State, and that's to vertically, you have multiple layers now. You have the coarse, median, or fine resolution. From there, we have test case running between 4 to 8, sometimes can up to 10 times speed up, basically more efficient compared to previous simulations. And also we have another version, it's ported to topography, and that's based on the curvilinear and grid, which is different. So it's not integrated yet. And we also run this year on Azure, and Harry is part of our, the project as the core PI. We have not done yet with the MVAPICH 2 Azure evaluation, but this probably it's to do that in the future. Yes. So now come with the weak scaling of the PLDC code on a different system, and we ported this code to the AMD GPUs using the HIP, and you see the linear, non-linear CPU, GPU, and the performance. The code scales pretty well, and it's on a system like AMD system. We were getting 32.6 petaflops, and the Texas scale they run on Frontier, we were getting 336 teraflops. That was on the CPU system. So now let's look into some PLDC performance with MVAPICH. So we revisit some communication work DK's group did, and we have a performance and communication issue in terms of system and the user memory overhead. And so other than the asynchronous communication and also the pre-posting, the approach we did, there was overlapping part is important. So that's what the DK's group come to help. And they did two scenario. Number one is using the non-blocking two-sided communication. So that increased the performance roughly by 11% when we test run a XT5. And but when we run up to more than 65,000 cores, and this performance degraded. And that's because of the skew created by the load imbalance between the bundling and the interior part for the calculation. And the other effort from the DK's group did is one-sided communication. That was running on the Ranger because the CREAM system was not able to take this advantage. So the one-sided communication also introduced roughly 10% performance gain. So that's together is I think it's 21% of performance gain using this overlap. So on the CPU side, the overlapping it's the last shopping of all the communications, as many of you know, and you try not to disturb the computation, the kernel computation. So every time when you change your code and when you do any optimizations, you have to touch the overlapping again. So that's part we find quite difficult on the CPU side. But on the other side, from GPU, and this overlapping with the multi-stream, the layers, and the copy communication, it's quite effective. And that's just my view. So this year, we test MVAPICH on both attack CPU system and also GPU system. This is running on the Frontier machine. I had only tested to up to 100 nodes. So far, we needed to now tune the code to running on a full machine. And the next Texas day run, I want to use the MVAPICH to run. So you see, with the latest MVAPICH, we are getting better performance. I do not remember how many percentage improvement we get. It's definitely better performance. So the other comparison is on the A100 nodes. This is on the SDC, the expense system. So with the default OpenMPI GCC compiler and compared to the MVAPICH, and you get a 20% of performance gain. On the Lone Star, it's similar. We get the MVAPICH has 20% extra performance gain. If we have the CUDA-aware support in with the GDR version, we get another 14% of the performance gain. So that's together is pretty good, and using MVAPICH, right, we get a much better performance. So that's the comparison. And the CUDA-aware support was implemented by the Decades group, and this is a part of the effort for the on-the-fly compression, and done by Tsinghua, and he did an excellent job and implement this part. Was as you heard yesterday from Decades talk, from Harry's talk, and this is it's IPDPS 2021 best paper finalist, and so this is the issue the PLDC code communication. The red color is quite 30% roughly the overhead, and this is what Tsinghua did. The way how he designed the on-the-fly message. You launch, you run the compression in the kernel, and then you return the compressor data, and then you start to send it to the header file to the receive side. At the same time, you also send remotely to the GPU the address. And then from the receiver side, you have the decompression, launch and run the decompression kernel, and then you store to the user buffer. So that's actually the concept from. So this work is completely done by the Decades group, and I provide only the source and also the verification, the scripts. So this is another figure showing about the MPC and the way how with data partition and the four streams, how this works. So you have seen these slides yesterday, and 35% of the performance gain using the CFP and the MPC was roughly 18%, in terms of flops. So this was done on the V100 system. And on the A100, actually, we were getting better performance. So this is some scaling I should put together, compare this in a different scenario, basically using different compiler level, and compared to the red color is default using the Intel compiler. So this is number is quite small. You probably will not see the details. But roughly, I'm getting 48 to 64% of the benefits using the on-the-fly compression with the MPC method. This is better than what we got from the V100. So I was, consulting with Tsinghua others, why we get better the MPC results than CFP. Probably they have better answer, but my understanding is compression rate is now better, and also the A100 has more computing threads. So, so overall, if you look at the Lone Star A100, so compare this Intel compiler, for example, here it's 16 nodes, it's 10.83 petaflops. Teraflops, and here now you get the 27.55. So that's 150% performance improvement. That's quite impressive. So what can we see from here? It looks like interconnect network is important, but the compiler, right, it's can make a huge difference. So before end of my talk, I want to talk a little bit about, at our PLDC, the software challenge, what we face. And we have now different versions of codes and maintained at the San Diego State, some SDSC, and some at the USC. And we have quite some issue. What we're trying to do now is merging these GPUs and the versions together. So that's going to be some work, particularly the topography version, because that is based on the curvilinear. And we want to also do the CICD, and we had some protocol done, a few years back. But this is lots of work. So we welcome the computer science students and with passion to support the real world like science codes and for a better the ecosystem development. So the other things we had Brownies and others talk about the energy efficiency in the previous talk. And the question is what motivated the users to improve energy efficiency, right? To us, it's more like about the time to solution. That's most, it matters most to us. And we recently look at the, the power consumption on the per motor machine. You have a pretty good occupancy, I would say, in terms of computation there. And the code is more balanced, right, in terms of, running during the time frame. So that come to the questions now about the inexact computing. This is quite a promising approach. People discussed in the last few years quite a lot. And that's for saving the energy. And traditionally, there's a line in the sand is not crossed between the application and also from the software stack. So from the software stack side, like on the file compression, for example, is one perfect example how you can reduce really the energy and improve the the accuracy. But I would say it improves the efficiency, and that's from the software side. But from the application side, there's lots of opportunities, right? Core design system and application. And for example, we did the discontinuous mesh. That's one example. And we need to also do the precision like reduction, error, like tolerance, and so on. So by the way, the PLDC code itself, as a final difference code, is quite efficient. And it's very fast, it's efficient, and it's pretty good fit for the regional scales, quick simulation, and also physics-based seismic hazard analysis. That's one I would say is a good example of inexact computing in the area. Yeah. So with that, I think I will stop here. This is a summary, about the project we will work with DK's group, and Stan already introduced before, and what we are going to do. And also we will work tech and the frontier, and the next generation system called Horizon, and to prepare our code ready on that system. So with that, I will give finally acknowledgement to my team. There's lots of people from SDC involved, contributed to this code. Amit here, Mahida, and there was one time in 2004 when we did the TerraShake, there was more than 30 people involved just in our center to contribute to support this simulation. You see how major the collaboration going on. We also have the collaborator from USC and from Kim Olsen, San Diego State. He is original LRP and code developer, and Phil Macklin is from SCEC Associate Director for IT. And also with the OSCU team here. Thank you.
Yeah. Thank you, Yifeng, for sharing these great results and insights. Do we have any questions from the audience? Okay, yeah. Can you please? Yeah, we have a mic for. Yes.
Yeah. Thank you. That's really interesting talk. And my basic question is about the model, different model itself. When you talk about what's that? A linear model, right? And then later on you get more sophisticated, more than just linear. And is that because you change the basic math model? What do you mean by linear? Is that a function? Whatever you're using is a linear function?
Yeah, but it's, you know, the code is still the same code and the final difference code. It's just adding the additional, you know, the components to the code for the calculation. Like we called this, at the beginning we started with the drag plug, and that's the nonlinear approach. It's adding extra into it. And then we have this Yifeng. This model was, you know, developed by somebody. It's from 1965. That's quite an old method, but it's not much realized at a larger scale. So that's the reason we added this drag plug into the code. But because this, you know, introduced like a multiple yield surface. The yield surface, that's, you know, very important. So if we have like 10 something, we will get a good performance accuracy. Okay. If we move to like 30, will be really good. Below 30 might not get much gain. And then we have a curve. Actually, we have a paper. So this year published about this nonlinear code using the Yifeng model. So this is quite, you know, latest, basically approach using, yeah.
Okay, so different models basically either improve your accuracy or improve your what's that? The quality of your service or something.
Yeah,
like
it improves the code accuracy quite some. For example, for the simulation we did for large simulation on the San Andreas fault, it reduced the ground motion by, you know, for the single layer one, we reduced by 25% in certain areas, and with the multi-layers, we reduced by factor 2. So altogether, that will make a huge difference. Basically, that means the linear approach, what we did, you know, several years back, was still not accurate enough. Particularly now, when we move to high frequency, we want to do the seismic hazard analysis, like, you know, for the engineer interest. And this one is not implemented yet. And like the CPA from the Southern California Earthquake Center, their program, and they are still using the linear solution now. And adding this one, because the issue is you add like 30 times more computation. And that's quite a challenge. So we need to get a balance. That's the reason we also want to introduce now the discontinuous mesh approach. So discontinuous mesh will have probably 10 times speed up. So then with the GPU, we have probably 5 times speed up. So then, computational nonlinear code will have 30 times more computation. Together, probably we still need like 2 times more allocation hours.
Yeah, so to my understanding, if I understand this correctly, first you want to looking at the problem itself. Okay, how do you get a better quality of resolution or solution?
Yeah.
The second thing is, from a different perspective, is with that kind of a challenge, what kind of method from a computing perspective to solve the different challenges? Like discontinued mesh is just the computing techniques for doing that, right?
Yes.
But does that leverage some specific characteristics of your problem in physics sense that actually help you?
Yeah. So, you know, there are many different codes in the community to do the similar simulation. You can use like discontinuous Garakin code, for example, and or continuous Garakin code. You can use the finite element code. There's many different codes there. Some are good in this area, some on other. That's what I showed. Some physics, particularly physics, were important. Like topography, for example, that's also play a role. And that's basically this is done by coordinated by Southern California Earthquake Center at the USC. They are the one to lead the consortium, and across the US and from different institutions. They're working to find the best, approach and also verify with the observed data. And so that's it's a huge community behind, design what is the best strategy. So at our PLDC code, it's unlike others. It's more efficient because in terms of time to solution, it's very fast. And also when you change it from like cybercheck and seismic map calculations. So when you change it from one mesh to another mesh, the new mesh, they can update very quickly. From other method, if you use the unstructured mesh, it could take you many months to prepare just update.
Data,
yeah. So that's I think this is the area there's lots discussion now when we talk about the inexact computing in the computer science, right? Yeah. So that's I think this is the way what is the trade-off, what is the balance, and accuracy is very important. And also we want to efficiency, right? So that's the way why we want to move up to the high frequency, because if you use the complex models, it will run like 10 hertz, it will take a long time. Exascale machine is not enough. This is, it doubled very quickly when you double the frequency, and you roughly 16 times, and the computation requirement will be required.
Okay. Now, Mike, take it differently. Do you have any idea what is your communication to computation ratio, based on whatever typical input data you provide?
Yeah, the computation ratio typically is 30%. But on the systems now, like when we run on the submitter machine, we scale this code up. You see the linear scale up. You do not see communication there. The reason is the network is very fast. We were able to hide this communication completely. But if it's a system like a PCIe, it's slower, you will not be able to really take this. You will see it like on the Lone Star, you see the performance will degrade. We only test on 16 nodes. If you run on up to a few hundred nodes, you will see the performance will drop quickly. So that's where the compiler can really play important. But this overlap is quite effective. And so far we see also good performance on AMD system.
Okay, now another question, sorry to continue on this, is what kind of a communication pattern do you use? Do you know that?
So,
whether collectives or mostly?
We have the point-to-point communications. Yeah.
By the code itself?
Yeah, correct, yeah.
Okay.
That's
have you ever explored the collective communications?
For using the A is MPI, basically, it's a point-to-point communication. It's just a ghost layer to change it. But data size is quite big. Oh. It's between the 6, let's say 2 to 16 megabytes, right? Tsinghua did some analysis. Roughly 2 to 16 megabytes, the message size. That's quite big. So that probably because we introduced I think probably, we should stop here for it. Yeah. So because we reduced the communication from 6 side to 4 side, that the volume is much bigger. So that's communication. The message size is quite big.
Yeah, it's a very interesting discussion, but unfortunately we're a little bit behind on schedule. So let's thank our speaker again for the great talk.